Hey everybody, it's Ripley again. We're on our last lesson. Woohoo! It's the end of Think. I hope you guys had a good one and a good time and learned a little bit about statistics, mostly statistics, a little bit of probability. Hope you enjoyed yourself. All right, we are in section 11.3. Look, the easiest way to do this is I'm simply going to do a problem for you. Again, it's going to be very much like the one in 11.2 because it's not very difficult, but to see it done out is the way to learn it. And we're going to do this with something called contingency tables. Contingency tables. All right, and I'm going to do problem number, let's see, we should do problem number 8 on page 577. This is going to be problem number 8. Okay, and so just take a minute right now, hit pause and read over problem number 8 for me. Okay, just give it a look-see, and I'll meet you back here in just a sec. Okay. Okay, hopefully you had a chance to look this sucker over. And basically what we're going to do, it's real simple. This is called a contingency table or a two-way table. Okay, and let's talk about what we're going to do first. What we're looking for here is we're trying to figure out if wins and losses, we're checking to see if wins and losses are independent of an open or a closed roof. Okay, so are wins, losses independent of roof status? All right, I'm just going to write roof. Or are wins, losses dependent? In other words, does the status of the roof affect wins or losses? All right, that's all that we're testing. We're going to use the exact same test called chi-squared, which we know is the sum of observed minus expected squared divided by expected, right? Exactly the same thing. Now, the degrees of freedom, let's look at this. In this two-way table, what we have here are columns, right? Columns go up and down like columns on a building, and we have rows, all right? Now, the degrees of freedom in any, if we're testing for dependence or independence, you can say it either way. It's easy. It's always the product of the rows minus 1 times the columns minus 1. So in this case, it's really simple. We've got degrees of freedom equals 2 minus 1 times 2 minus 1. That's affectionately known as 1. All right. Now you may say, well, Ripley, what if there's not, if I'm missing a column? Well, then we're doing just a regular old chi-squared, and we're going to check for certain proportions in each of the wins and the losses. All right. Now, excuse me. So we're going to test this thing, I forget, in the problem. Yeah, the problem says we're going to test this guy at alpha equals 0.05. Now, let's talk about assumptions always. All right, assumption. Whoa, assumpts. Perfect. Assumpts it is. Yeah, it's the end of the semester. Leave me alone. The assumptions are exactly the same as goodness of fit. All right, in other words, of goodness of fit. In other words, we're going to have frequencies. We are randomly selecting values, although the values are already there. I don't like that this author chooses to write randomly selecting values. It's not as though we selected the values. What we did is we just stumbled in and we said, okay, we're gonna tally these frequencies. Okay, excuse me. Remember, so let's write them up. Number 1, so simple random sample, but I'm going to put a question mark there like, what does that really mean? Okay. Number 2, we're going to have frequencies in cells. So in other words, discrete numbers, frequencies in cells. And then last but not least, expected values in each cell each cell greater than or equal to 5. Okay? All right, so the first thing that you want to do, I'm going to change colored pencils because or the color of my pen, because this is pretty important. The first thing that we want to do is we want to sum everything up. So I've got 51 in the first column, I've got 28 in the second column, I've got 53 in the first row, and I've got 26 in the second row. Now, we want a total here, and I'll show you why here in just a sec. We'll plug this in. You know what? I'm going to need to give myself just a little bit more room, and you'll see why in just a sec. Because you may already be a little suspicious. What did we say that this was? This was 53. This was 26. Gives me a total of 79. They both add up to the same thing. That's good. All right. Now you may say, what are these expected values? These are observed values. Those are just the values that go in, just like normal. But you may say, wait, where am I going to get my expected values from? Well, the expected values are actually really, really simple. The expected values for any cell is simply equal to, you ready? All I do is I take the total for the row that cell is in. I take the total for the column that cell is in, and I divide it by the total number. All right? So I'm going to do these over here. For those of you that might remember matrices,